Using the natural coordinates, we found out the shape functions n1 and n2 as n1 equals to 1 minus zeta upon 2 and n2 equals to 1 plus zeta upon 2. Here we are going to find out the variation of n1 and n2. So we have a bar element having nodes 1 and 2. The zeta coordinates vary from -1 to +1. At node 1, zeta equals to -1. Substituting this in the formula for n1, we get 1 minus of -1 upon 2. This equals to 1. Similarly, n2 equals to 1 plus of -1. This will give us 0. At node 2, zeta has a value of +1. So substituting here, we'll get n1 equals to 0 and n2 equals to 1. Let us draw the variation of n1 and n2. So this is a variation of n1. These are the nodes 1 and 2. At node 1, n1 equals to 1. And at node 2, n1 equals to 0. Similarly, if I am drawing the variation for n2, at node 1, the value of n2 is 0, and at node 2, the value of n2 is 1. So this is a variation of the shape functions n1 and n2. So far what we have derived is, if we want to find a displacement at any intermediate point within the element, it can be given as n1 q1 plus n2 q2. Similarly, if we want to find out the coordinate zeta at any point in between the element, we can represent that as zeta equals to n1 zeta 1 plus n2 zeta 2. So notice here that the same functions n1 and n2 are used in both the equations, whether we want to find out some intermediate displacement or intermediate geometry as well. Okay. Since the same parameters are used for both the conditions, n1 and n2 are also called as isoparametric functions. Iso means same. So the same set of functions are used to define displacement as well as geometry. So isoparametric elements use the same set of functions, or also known as shape functions, to represent the element geometry as well as the displacement. Next, we will see the relation between the Cartesian coordinate and the natural coordinate. So we have 1 and 2. The coordinate here is x1 and at 2 it is x2. At any point x, and the length of this element is L. L can be given by x2 minus x1. The geometry of a point within the element can be given as Okay, so now we want to find out the location of this point, the geometry of this point. It can be given as x equals to n1 x1 plus n2 x2. The strain displacement relation is given by epsilon equals to du by dx. In one of the lectures before, we had derived the relation between the natural coordinate zeta and the Cartesian coordinate x as follows. So now if we want to differentiate this with respect to x, we get d zeta by dx equals to 2 by L. L can be written as x2 minus x1. Using the chain rule of differentiation, okay, so epsilon can be given as du by d zeta into d zeta upon dx. We know that u is given as n1 q1 plus n2 q2. Let us substitute for n1 in this. So we have 1 minus zeta upon 2 into q1 plus 1 plus zeta by 2 q2. If we have to differentiate this with respect to d zeta, we will get so du by d zeta can be written as minus q1 plus q2 divided by 2. Substituting this in the epsilon formula, so we have du by d zeta is minus q1 plus q2 upon 2, and d zeta by dx is 2 upon x2 minus x1. So we have 1 upon x2 minus x1 minus q1 plus q2. This is of the form epsilon equals to b into q, where b is a 1 by 2 element stiffness, element strain displacement matrix. Which can be written as 1 upon x2 minus x1 minus 1 plus 1, and q is the displacement matrix which is given by q1 into q2. So we can write epsilon equals to 1 upon x2 minus x1 minus 1 q1 q2. In this equation, this term here is the displacement matrix B, and this is the displacement vector Q. Please note that the use of linear shape functions results in constant B matrix, and hence the constant strain is obtained within the element. Okay, from Hooke's law, we know that stress is given by Young's modulus into strain, or we can also say, we know that epsilon is B into Q. Okay, so stress is given by this, and the stress also given by this will be a constant within the element. The expressions of U equals to N into Q, or epsilon equals to B into Q, sigma equals to E, B, Q, relate the displacement, strain and stress respectively in terms of nodal values.